Do people in the room know what that is? Z-scoring? Can I just put up your hands? I just don't need to, okay. Enough people don't know, I'll just explain here. So what a Z-score is basically this, right? You know, when you collect data, like any kind of data, you know, it's going to have some distribution, right? So let's say I just draw a histogram, a very simple histogram of all the measurements I had for the accelerometry. And it's way the hell out here, right? And then I collect all the things that came from the temperature sensor. And they were all like clustered over here, okay? Well, if I want to compare these two things, I sort of want them on similar scales somehow. Because when Tuka showed you that bar plot, remember she said, oh, this one's 3, and therefore it's bigger than this one, which is 2, and therefore bigger than this one. So there has to be some way of scaling them so that you can do those comparisons, right? Mm-hmm. And if you have the distribution so crazily like this, it'll be reflected in those coefficients, and you can't compare anything. So what z-scoring does is it drags this thing, centers it on 0, and makes it standard deviation 1. That's what it does. So you're just getting this guy, you're literally pulling him here and then shrinking him so that he's 1. And once you've done that for all of the different things that you collected, the features, now you're comparing apples to apples. You can know for the coefficients that you get in your model whether this one is in fact more important than that one because they're all on the same scale. Does that answer your question?
Yeah. Does it mean the data is from a different family of distributions?
Does it model if the outcome that you're modeling? So, well, for a linear regression framework?
Because like you said that, like for the model, of course, every data has a distribution. But like for linear regression, you assume the error has a specific distribution, right?
Yeah, you assume that the residuals are normally distributed,
yeah,
and that also counts for logistics. Yes.
But normal data not always going to be the case. Maybe like some data is exponential distribution. I don't know.
Yeah, then you can log transform it.
Okay, okay.
Yeah, you can log transform it. But actually, to be very clear, the regression frameworks only assume that the residuals of the model. Does everybody in the room know what a residual of a model is? Can I see it? Show hands. Oh, just a couple. So I'm going to explain it again. It's actually quite simple. A residual model is okay. So let's say I have a linear regression. Let's assume it was, you know, for this model, instead of giving a 1, 0 and using logistic, I capped it between, and I gave a number between 0 and 1, okay? So let's say I had some points like this, and then I fit a line, okay, like this. The residual is this error. How far off, for every sample that was in the data, how much error did I have in my prediction? What you want is if you then say, okay, each of these is 1 point, I can construct a histogram from that. The assumption of linear regression is that that's normally distributed. The errors that you're having, which is called residual, is normally distributed. So classically, the way that you help guarantee that is you try to condition the outcome to be normally distributed, right? But in the case of a logistic regression, it's not normally distributed. It's a bimodal, it's a binomial distribution. So this condition is all you have to check, right? You don't have to worry about any of the inputs, and in our case, it's fine. Does that answer the question? Yeah. Yes?
I have experience with kind of manually making models with logistic regression, so I'm not sure, how do you go about in machine learning, like trying to get it to figure out its own like parameters, like I've gone through, I don't know, like, you know, forward selection or a selection procedure myself of certain variables, and then based on knowledge of the system, I take out and I put in and I keep whatever, but it seems like here, the machine figures that out for you, right?
Yes, that's right.
Okay, I'm not sure if how does it do that? Is that like, it pulls out things, it puts it back, and it's through the AUC?
Yeah, so actually, that's, I think, let me return back to these. Let me return back real quick. Hold on, just one moment. Let's come back up here. This is meant to showcase sort of how that works. So, look, let's assume that I'm going to build a logistic regression model, and there's only, I'm only going to put in one feature. I've decided. I only want to put the most important feature because I only want to build with one. I mean, let's say you're doing cell biology, and you know you're going to, at the end of the day, you might look at something about the cells. You might extract some features, like we were speaking about earlier. How much does the bacteria wiggle when it goes, or you know, how big is it? What's its diameter, or whatever? There's some features you're going to extract, and you're going to say, now I want to use these. I want to put them in a logistic regression and figure out infectious or not. Okay, that could be the outcome. 1, 0, infectious or not. Okay. So the thing is though, like you said, you want to have a principled way of selecting out of these, let's say 10,000 things that it could possibly be that you thought of as candidates. You have to select a principled subset that are useful for your prediction later. This process says that what you do is you just grab each of them individually and you train one model with just that one feature. That's it. Okay? And then what you do is you say, okay, this one did the best. So now I'm going to train a model with two features, but making one of them this at all times. Does that make sense?
Okay.
And then you repeat this until you get some saturation. So look, for this first one, what happened? It was 90. Well, so obviously when you add another feature, it's going to move up from 90. It's not going to move down, right? Is the idea. If it moves down, then you're done. Does it make sense?
Yeah.
And also, if it's only increasing ever so slightly, right? Like if you're getting 0.001 improvement by adding that next feature, then why the hell would you add it, right? You're just squeezing more features in for a tiny, tiny, tiny amount of improvement. So that's how you naturally just stop forward selection.
Okay, yeah.
You know, because the improvement in the performance is going to be like this. So if this is the number of features, let me show you here real quick. If this, let's say the number of features is here, and let's say that the performance is here, okay? So what is it going to look like? It's going to do this. So you stop like, okay, here, right? You know, you don't like squeeze it when it's all the way out here, right? And keep adding, right? Yeah. Does it make sense?
Did you guys use, I'm not sure what the difference was between like an AIC versus an AUC, like an IKK?
Yeah, a Conke's information criteria, here's what you do. So a model, remember we spoke about residuals? Okay, residual says something about the deviation between what was predicted and what was not there. A Conke's information criteria takes that and it says, here's the error that the model produced in a linear regression, let's say. There's some error. But then here's what I'm going to do. I'm going to add extra penalty. I'm going to hurt you the more features you throw in. So what that could mean is that if you add 2 more features, I'm going to punch you even harder now for that same level of error.
Okay.
Because, like, what is this? You had 4 features, you had 4 things that you used, and you had the same level of error as a guy who had 2? Well, then clearly the guy who used 4 is worse. It's like a Rube Goldberg machine, right? You know, like, it penalizes the Rube Goldberg machine approaches. Okay, so in our case, though, what we cared about was the classification performance of the model, right? So we used the area under receiver operator curve. That's what it tells you. How well does it classify? Whereas AIC is going to tell you, is this model kind of, you know, for the amount of error that it's producing, for the amount of error that I'm seeing, you know, is the number of features justified? So it's trying to prevent the Rube Goldberg machine. Everybody knows what Rube Goldberg machine is, I think. Those crazy contraptions that move a ball from one end to the other. You know, with a shoe in it and a Ferris wheel, right? You know. Other questions?
Yeah, suppose that you have like this 1, 2, 3, 4, 5. These variables that you have there, and one of these variables is a function of the other variables.
Yeah.
It's linear dependent. So when you do the first testing of the model, you find the first variable, this is really good. And then the second one, the thing that's going to be a bias, and choosing the one that's linear dependent of the other one, because the first ones are really good, so the second one should also be really good because they're not independent of each other, so it will be a kind of a bias on selecting.
So highly collinear features, which is what you're speaking about.
Yeah.
Collinearity is when in a data set you have, okay, let's say when a bacteria wiggles more, it also happens to be bigger. Okay, that means that it's collinear. As this one grows, this one grows. So what would you expect then? If those two are strongly linearly dependent, then actually when you're doing this process, you're running through and trying to see, given this one, what improves, that guy's going to provide no additional information. Because all the information is already captured in the function, right? I already knew that when he wiggled more, he grew bigger. So what does knowing bigger, how does that help me? It doesn't help me. So this process accounts for that. Does that answer your question?
Yeah.
So that's a note. When you go to the neural network and you have some of them bypassing, like maybe the first few nodes,
Yes.
is that because it's just like most of like I don't want to say
This-
heaviest, yeah. So how do you use the one that goes to the I don't know, top circle? Because like it's just the best predictor for the.
Yeah, so effectively what you do, and this is the thing that, at my request actually, Tuka skipped over, so I'm sorry, Tuka. We could have nipped this. Look, when you have, you could take, this is like, where do you introduce the string, right? In the string when you want to bend it, right? How much, there's 3 pieces of string down here, all 5 down here, right? It's really that question. Because typically with neural networks, you throw everything here at the bottom. And actually, this is sort of a frontier of neural network science. Nobody knows if it does better by putting it up at the top, because nobody really knows why they work better in many cases in the first place, other than the fact that they can bend the line very effectively. So we basically just randomly popped these things in places and then said, how well did it do? Let's take the one that did best. And that thing that popped out was this. So it's just random. I mean, there was no sort of, oh, let's be strategic here, like the forward selection and, have a principled approach. It's just statistics, right, that led to this configuration.
Did you base that on like performance of the neural network or the final answer?
The performance of the neural network on the training, not the final answer. Right, on its training, yeah. Because if you base it on the final answer, then you're just dead in the water. Because, yeah, of course, if you roll a dice 5,000 times, right, you're going to get any number you want, right? It's going to pop out the other end. Yeah, so that's a good question.
Does it, I don't know, like now, you two, like checking out the data now, like, I mean, this figure eight, does it make some sense, like, to why those features are on top and why something?
Can I have the, oh, it's here, sorry. Okay, so let's go through them. What do you know, so I'll point out a couple things here. This PPG signal, this is the raw measurement of the, basically as your skin changes color due to a pulse, that's what this is. It's just a very raw measurement, okay? This is a low, very raw measurement of the energy in your voice. This is accelerometry, another raw signal. So they get placed towards the bottom. Why? Because ostensibly I need to bend those lines more to get use out of them. Because they're very raw. Whereas look at this one, negative sentiment. Well, that's kind of, clearly that's obviously related to the output, so I don't need to process it much. So where does it get placed? It gets placed towards the top. Does that make sense?
Yeah.
So there is is it perfect? No, it's not perfect. But there is some kind of pattern here that makes sense. You see it, right? The things that are more abstract get placed higher. The things that are more raw get placed in the middle. Look at this one, for example. This is the difference between two things that were like this. That's a bend, right? So where did it get placed? Instead of getting placed at the bottom, it got placed one layer up. Right? So there seems to be that pattern is there, but I wouldn't tell you that I know that for sure, right? Like whether if you ran this experiment and you optimize it forever, whether this is the perfect configuration. You just don't know. Yes?
This kind of leads into a question about the data set itself. This seems to have some pretty cool information in it. How many people were in the original data set? I think
just 10.
10?
Just 10.
Was it kind of like just graduate students who were like going through a specific set of like predetermined, like, hey, read this story or come up with your own story?
No. It was intentionally extremely unstructured, but the caveats, and we have to be modest about this as well. So although it was unstructured, so we said there's no time limit, tell a story as long as you want, tell the story about whatever, you just completely unprompted, literally like if I told one of you, just tell me a happy story, like that. That was the instruction. And then you have an iPhone sitting on the table recording the audio, and they're wearing a watch. That's the experience. But look, we're collecting it from people who are attending a university campus. So they're between a certain age range. They're between the age of 20 and 32, let's say. Okay? They're going to come from probably certain socio-economic backgrounds, right? So if I took this and I went to a radically different location than a college campus, would it translate? In its current state, probably not. It wouldn't. But what this actually stands to show is that you can actually, with a very small number of people, create algorithms that generalize to a greater community of peers. People in this room could collect some data on a small number of you, and ostensibly, as long as you're more similar than you are different in some of your communication aspects, you could take that algorithm and deploy it on other people in your university, right? And try to do you sort of follow the,
Yeah, I've currently been doing a little bit of data collection, and it seems like I'm a little bit curious about some of the processing of that data. Now that I know that you actually went out and got that data, like accelerometer values, were you just feeding in just raw numbers into the model, or did you do some type
No.
of processing on that data?
no, let's go back here.
You're just literally throwing it in.
No, you don't, we don't just throw it in. So there's a, let me just show you real quick. Okay, here we go. So,
Oh yeah, so feature extraction.
yeah,
from the raw
so,
data.
so what you do is from an accelerometer, you take mean, median, variance. first.
Kind of over the whole data set or for chunks of it?
It depends on what you're trying to predict.
Okay.
Right? So in this case, if you, so there's a nuance here. What the short answer is it's in 5-second blocks.
Okay, that's
But
what.
then if you want to, predict for a whole conversation, after the class, so this classifier is going to give you a prediction on each of the 5-second blocks. You can average across those to get a single score at the end. You get it? Versus if you want to do it within obviously a low resolution time frame, then you're going to just have one. There's no averaging. You just get the probability from that time block.
From that exact.
You got it. Yeah, you got it.
So you could potentially do it like over the whole like 2 minutes of the narrative. The reason we chose 5 seconds